book derives a couple of equations for a specific elastic collision. The conditions are that the collision is head-on, so it's not hitting at the side. For example, the bowling problem we did, where the ball hit at the side of the pin, so the pin took off at an angle. These equations I'm going to give you are not valid in a situation like that. The equations I give you, they have to hit head-on, so straight on to each other, and one of the objects needs to be at rest initially. So, for example, if we have two balls, mass 1 is traveling with some initial speed. Mass 2 is at rest. So the ball hits head-on, the result of the collision. Now, the ball 1 could end up moving to the right, it could end up moving to the left, it could end up being stationary. It depends upon the masses of the balls. I'm going to draw it to the right for the moment, just to indicate that it has some sort of final velocity. Ball 2 will also have some sort of velocity. The motion will take place along a straight line because the collision is head-on. So none of these objects are going to take off at angles. The equations we have that are valid is momentum. M1 V1 initial is the total momentum of our system initially. That has to equal M1 V1 final plus M2 V2 final. The total momentum of our system finally. The objects do not stick together. If objects stick together, then it is an inelastic collision, which is a completely different story. So elastic collisions, the objects never stick together, they just bounce off of each other and keep going along their merry way. So momentum is conserved. In elastic collisions, the energy must be conserved as well. That's what characterizes an elastic collision. So the total kinetic energy our system has initially, well, ball 1's the only one that has kinetic energy initially because it's the only one moving. That has to equal the total kinetic energy that our system has finally. Both balls will have some kinetic energy. So we have two equations and two unknowns. So basically, if we solve, for example, for V1 final and plug it in our second equation, we will get an equation for V2 final. I'm not going to go through all the algebra. So the final velocity of ball 2 depends upon the masses of the balls and how fast ball 1 was moving initially. Plugging that back in and solving for V1 final, we get an equation for V1 final. If the masses are the same, for example, pool, billiards, if the masses are the same, the first ball will stop. Now that's assuming no spin on the ball. Okay? You play pool and you put spin on the ball, that changes things up. This is a nice straight line. If you hit it nice straight line, no major spin on the ball, the cue ball will stop, and whatever ball you hit will keep going. The ball will keep going if the masses are the same, at the same speed the original ball was going. So if the masses are the same, the original ball that was moving stops, the second ball starts to move and continues moving at the speed that the original ball was moving at. If the masses are not the same, you just got to plug them through the equation and you can figure out the speeds and so forth. Okay. Now I mentioned that ball 1 could rebound backwards. When would that happen? If mass 2 is bigger than mass 1, exactly, we're going to get a negative answer here. So V1 final will be negative something V1 initial. That means it's headed in the opposite direction. So if mass 2 is bigger than mass 1, your original ball will rebound and head backwards. Notice though, V2 final is always going to be positive. So V2, mass 2, will always travel in the same direction that the original ball was traveling in. If you have any other situation, if you do not meet these conditions for your problem, you need to set up the equation specific to the problem and solve them from there. Okay? But you have a couple of problems on your homework that do meet these conditions, and so you can use these results to answer the questions. And that will be just fine. So please keep in mind, if you have a collision of any sort, momentum, momentum, momentum. Momentum is always conserved in a collision, regardless of the type of collision it is. Energy, you have to think about. You have to think, was any energy transferred to some other form? Was there friction of any sort? Was there some sort of push or pull that could have changed the energy? So energy you have to think about a little bit more.